This classroom lesson is a cooperative effort between the Wisconsin Public Service SolarWise for Schools program and the Create Energy Center. What's on our roof? Prep for success. Introduction and lesson objectives. Welcome, students and teachers, to What's on Our Roof, a series of lessons in which you'll learn from the photovoltaic performance data produced by your solar array. This is Lesson 2, Prep for Success. In this lesson, you'll visualize and learn principles, concepts, and vocabulary that prepare you for success in the lessons that follow. We'll begin this lesson with a review of electrical power and electrical energy from Lesson 1. Then you'll relate power and energy to an output profile like those you'll see on the interactive graphical interface that displays your solar PV data. We'll review Earth and space science concepts that enable your array to produce electricity. You'll learn how to describe the position of the sun in the sky using the key vocabulary terms of solar azimuth, solar altitude or elevation, solar noon, and solar window. You'll relate this information to PV array positioning and why an array produces electricity differently at different times of year and different times of day. Finally, you'll begin to interpret the effect of weather on a daily solar PV output profile, a type of profile you'll be using regularly from the lessons that follow in What's on Our Roof. But first, before getting into the lesson, there are just a few baseline items to review. First, we all know that the sun doesn't revolve around the Earth. However, we may refer to the movement of the sun across the sky in ways that make it seem that way. You'll probably talk about it that way too. But the sun doesn't revolve around the Earth. Rather, the Earth revolves around the sun. And, as you should know, Earth's revolution around the sun, coupled with its 23.5-degree tilt, causes our seasons to change. And as you should know, the change in our seasons drives the changes in our weather. We'll be studying the effect of both seasonal differences and weather differences on solar PV output and output profiles in Lesson 2 of What's on Our Roof? Prep for Success. Electrical power and electrical energy defined. Let's begin Lesson 2 of What's on Our Roof right here. This is a solar PV output profile for a very sunny day. It's like many you'll be producing and interpreting in this series of lessons. Output profiles like these always give you measures of both electrical power and electrical energy. As we trust you remember from our introductory lesson, electrical power is the rate at which energy is transferred in an electrical circuit. An instantaneous measure, the kilowatt, kW, serves as the standard unit for expressing electrical power. Electrical energy is the ability to do work that results from the flow of charged particles such as electrons through a conductor. The kilowatt hour, kWh, serves as the standard unit for expressing electrical energy. It's a measure of the total quantity of electrical power a system either consumes or generates over time. Electrical power and electrical energy on the solar PV output profile. Now let's tie the output measures of electrical power and electrical energy to this solar PV output profile from a very sunny day. Here are 9 data points selected from thousands of data points taken during the day and displayed along the dark green plot line. The first data point at the bottom left of the graph is from 12 a.m. The next is from 3 a.m., then 6 a.m. You can probably guess why the next data point begins to climb from the bottom of the graph. It was taken at 9 a.m., then 10:30 a.m., 12 noon, 1 p.m., 3 p.m., and then at 5 o'clock in the afternoon. Plainly, time is the variable that's plotted on the x-axis. Time is the independent variable on the graph. It stands alone and doesn't change in response to what we're measuring. That makes power in kW the dependent variable on the graph. Plotted on the y-axis, the dependent variable, power, is what's being measured. Power depends on the independent variable. The electrical power produced at any instant by a PV array is usually expressed in kW. The kilowatt, kW, plays a significant role in our daily lives. It serves as the standard unit for measuring electrical power. The kilowatt comes from the unit, the watt, capital W. A watt is an electrical power measurement unit named after Scottish scientist James Watt. The common use of the kilowatt, 1 kW equals 1,000 watts, is due to the very small magnitude of the watt as a unit of power. Most appliances in a home use electrical power quantified in watts. This is the electrical power required at any instant for an appliance to operate. On our solar PV output profile, it's the power produced at any given instant. Returning to these data points for a moment, we know these are just 9 data points measured among thousands of data points taken at various time intervals. Put all of those data points together and the graph looks like this. But what does this area under the curve represent? It represents energy produced in kWh. The kilowatt hour, kWh, is a unit of electrical energy. It's a measure of the total quantity of electrical power a system either generates or uses over time. Power multiplied by time. Although it may seem like a time measurement, the kilowatt hour actually represents a quantity of energy production or consumption. You can visualize it on our graph this way. We'll place a grid over the top of this graph. Each block represents a quantity of energy. The blocks with green in them represent a quantity of energy produced by this solar PV array. As you can see, 1 kilowatt of power extends along the y-axis from the baseline to this midline. Anytime a second kW was produced, that power is shown above the midline. Time is shown along the x-axis. Each block of energy is divided into 1-hour time segments. As a result, each block represents a quantity of energy defined as 1 kilowatt hour. Power multiplied by time, or kW times H, or just kWh. What is the total quantity of energy produced? Recall that the green area under the curve represents energy produced. Since there are 8 blocks completely filled with green, that represents 8 kilowatt hours. Add in the green energy production from 15 other partially filled blocks, 7.6 kWh, and you get a total of 15.6 kilowatt hours kWh of energy produced by the solar PV array on this sunny summer day. The total quantity of electrical energy generated over time is usually expressed in kWh. It's easy to get kilowatts, kW, and kilowatt hours, kWh, confused. They are closely related energy units. But a kW is a measure of electrical power, while a kWh is a measure of electrical energy. The kilowatt is a measure of electrical power generated or used at a given instant in time. The kilowatt hour measures a quantity of electrical power generated or used over time. The kilowatt hour, kWh, is not only the primary unit used to measure electrical production or generation. It's the primary unit used to measure electric consumption. On your electricity bill, the kWh is the unit used to charge for the quantity of electricity you consume. And in case you forgot, as a reminder, a helpful way to think about the difference between electrical power in kW and electrical energy in kWh can be found in this simple comparison to running water. Power in kW is comparable to the flow rate of the water. Energy in kWh is comparable to the quantity of water in the bucket. Array orientation and sun position. Now it's time to take you to a school rooftop. You'll probably never be permitted to visit here, but if you did, you might not be very impressed. A solar PV array just sits there during daylight hours and produces electricity, minute to minute, day to day, month to month, and year to year. You might be bored watching it work, but there's nothing boring about what it does. We'll assume you know that solar panels need sunlight to produce electricity. The more unshaded direct sunlight, the better they work. That's why installers do their best to point or orient a solar array to face due south. From our point of reference on Earth's northern hemisphere, the sun spends most of its daylight hours in the southern sky. A well-installed fixed array, pointed due south, tilted up to an effective angle, with little or no shade, will produce electricity at or close to its maximum over its lifetime of 25 to 30 years. The school rooftop solar PV array you see here is the very same array as this one. But this photo was taken from behind the array in panorama setting. As you know, the panorama setting distorts a photo, but it gives us a photo showing a much wider sweep of sky in front of the array. From behind, the school array you see here is oriented or pointed due south. Off this edge of the array is due east, and this direction is due west. And here is your last reminder that the array you've been looking at from behind actually looks like this. Now let's do a quick review of how these three directions are designated on a compass dial. On a compass, due south is 180 degrees, due east, 90 degrees, and 270 degrees is due west. Now if we lay the compass flat on the ground, due south, or 180 degrees, is straight ahead of the array. This array is well positioned to get lots of sun since it's pointed or oriented where we find the sun, in the southern sky. To the left, Straight down this edge of the array is due east, or 90 degrees. And directly across the array down this edge is due west, or 270 degrees. Taking our compass away, with a little imagination, we can add a few more compass degrees along the horizon. You'll be using compass degrees like these to designate the position of the sun across the horizon. This is called the sun's azimuth. Here are some random places we might find the sun in the sky. Each can be described with a compass azimuth degree: 90 degrees, 120 degrees, 180 degrees, and 270 degrees. Here's your definition for solar azimuth. Solar azimuth is the compass degree 0 to 360 that describes the position of the sun along the horizon at any given time. Now we'll put a different set of suns in the sky. As you know, there's a solar azimuth degree associated with each of these sun positions. But there's another degree associated with the position of the sun in the sky. Many people say it's how high in the sky the sun is. It's the sun's altitude, or elevation. Here's your definition for solar altitude or solar elevation. Solar altitude or solar elevation is the vertical angle formed between the horizon and the center of the sun's disk at any given time. Solar azimuth, the compass degree 0 to 360 that describes the position of the sun along the horizon at any given time, and solar altitude or solar elevation, the vertical angle formed between the horizon and the center of the sun's disk at any given time. These are the two compass degrees you'll be using to describe the position of the sun in the sky at any given time. More solar vocabulary and the seasons. You've probably noticed these sun positions aren't randomly placed in the sky. They've been placed to represent the movement of the sun across the sky during the day. Of course, this is sunrise, shown at 90 degrees azimuth and 0 degrees altitude here. And this is sunset, shown at 270 degrees azimuth and 0 degrees altitude here. But this particular position of the sun in the sky, as you might expect, is of very special interest to us. The sun is at its highest point in the sky here, its maximum altitude or its zenith. At this position, the sun is due south, an azimuth of 180 degrees. When the sun is here, the time of daylight up to this point equals the time of daylight after this point. This position of the sun in the sky is called solar noon. Solar noon is the moment during the day when the sun reaches its highest point in the sky, its maximum altitude or zenith. The sun is due south. Its azimuth is 180 degrees on a compass dial. And the daylight from sunrise to solar noon is equal to the daylight from solar noon to sunset. Solar noon is usually close to, but is seldom the same as clock noon. This is because of daylight savings, or your location within a time zone, etc. Now let's add a few additional sun position markers. Sunrise, sunset, 9 a.m., 3 p.m. We'll say this is a sun path profile for the first day of spring or vernal equinox, and the first day of fall or autumnal equinox, at roughly 45 degrees north latitude on the globe. Sunrise occurs at an azimuth of about 90 degrees. Sunset occurs at an azimuth of about 270 degrees. Solar noon occurs at an azimuth of 180 degrees. And the sun's altitude or elevation at solar noon for the first day of spring and the first day of fall at roughly 45 degrees north latitude. Its altitude is approximately 45 degrees. And on this day, there are approximately 12 hours of daylight, about 6 hours before solar noon and about 6 hours after solar noon. Keeping in mind, this is a rough profile for the first day of spring and the first day of fall at 45 degrees north latitude. We'll remove a lot of detail and clean up the illustration before adding another sun path profile. This one. For this sun path profile, the sun's altitude angle at solar noon is approximately 20 degrees. And on this day, there are approximately 8.5 hours of daylight, about 4.25 hours before solar noon, and approximately 4.25 hours after solar noon. Can you puzzle this out? This is a rough profile for the first day of blank at 45 degrees north latitude. It's a rough profile for the first day of winter at 45 degrees north latitude. Again, we'll remove detail, clean up the illustration, and add another sun path profile. For this sun path profile, the sun's altitude angle at solar noon is about 70 degrees. And on this day, there are approximately 15.5 hours of daylight, about 7.75 hours before solar noon and about 7.75 hours after solar noon. Can you puzzle this out? This is a rough profile for the first day of blank at 45 degrees north latitude. It's a rough profile for the first day of summer at 45 degrees north latitude. The first day of summer, first day of spring and fall, the first day of winter. Adding a little detail back in enables us to sketch in and visualize an important concept. This area of the sky represents all the locations the sun can be found between 9 a.m. solar time and 3 p.m. solar time for each day of the entire year at 45 degrees north latitude. It's called the solar window. What is the solar window? Solar window. The critical hours of 9 a.m. solar time to 3 p.m. solar time that are the most important for the conversion of sunlight into electricity for a well-positioned, fixed solar array. The solar window will be the focus of a whole lesson you'll soon complete. Weather and the output profile. The differences in daylight each day of the year and in the length of the solar window each day of the year are a product of change in the seasons. Each day the Earth revolves around the Sun at its 23.5 degree tilt. This means the distribution of the Sun's energy across the surface of the Earth changes every day. This causes the gradual change in the seasons. And that makes the Earth revolving around the Sun at its 23.5 degree tilt, causing the gradual change in the seasons, a primary driver of weather patterns and daily weather. Let's evaluate the effect of weather on this solar output profile for a very sunny summer day. If this day was sunny with no clouds at all, the profile would form a smooth parabola that opens downward. But this output profile plot, this parabola, is not perfectly smooth. Can you explain the slightly ragged parts? You probably figured it out. There were light clouds in the middle of the day. Can you draw some general conclusions about the weather from this day's output profile? This part's easy. It was sunny until this part of the day, sunny after this part of the day. And here, becoming cloudy, then darker clouds, very dark clouds, probably a storm. Clouds getting lighter, lighter still. The day in general, and the effect of weather on a solar PV output profile. In review, the weather, the seasons, solar window, solar noon, solar altitude, solar azimuth, electrical energy, and electrical power. This has been Lesson 2, Watts on Our Roof. Prep for success. Now, complete the exercises for this lesson. Then move on to Lesson 3 of Watts on Our Roof.